evening, everyone. Welcome to this webinar. I'm Walid BouCenna, and I will be your host. I'm proud to be your host. This webinar will be about BGP, fundamentals, and configuration. So this is a little about me. So I'm Walid BouCenna, and I work into a HALP, so Huawei Training Official Partner. I'm the winner of the ICT competition last year. I have Huawei Certified Instructor certification and Cisco Certified System Instructor certification. I'm both SCIP and CCNP. And this is my LinkedIn if you want to make connection with me and if you have question after this webinar. So let's get started. So this webinar will be about BGP. So BGP is a very large topic. We can't cover everything in 1 hour. So I'm gonna focus only in the basic of BGP. And so after this webinar, you will understand what is BGP and how BGP work. So you can go to much detail after this webinar. So in the first, we're gonna see BGP overview. We will see what is BGP, why do we need BGP, and we will see that BGP has two neighborship, eBGP and iBGP. We will see the path selection of BGP and the metric of BGP, that is BGP attribute. In the end, we will do a lab and we configure BGP in Huawei router. So why do we need BGP? So this network represent the internet. Internet is more than this network. Internet represent 1,000 or more router. So why do we need BGP? Why we don't run just OSPF or ISIS in all the internet? So if we run OSPF in this network, so OSPF need to store all the information in a database. This database is the link state database. So the internet has more than 1 million routes. So OSPF can't handle this number of routes. So this is the first problem. So IGP like OSPF and ISIS can't handle this number of routes. The second problem is that the internet is unstable network. There is no stability in internet. So link flap everywhere in the internet. And IGP, when there is a link where a link flap or route are discarded, so each IGP need to reconverge, because IGP like OSPF and ISIS need to have rapid conversions. So if we run OSPF in the internet, the network will never converge. So the second problem, running OSPF in the whole internet, so all ISP need to have the same routing policy. So ISP A and B need to have the same policy because they share the same protocol and they have share the same protocol. So this is why the inventor of the internet, or lastly the ARPANET, said that we will segregate the internet or into multiple IS. So every company or every service provider we have will be an IS. So the IS is the autonomous system. So when we segregate the internet into multiple IS, so every company will have, or every ISP will have his routing policy. So inside the ISP, every ISP will run its favorite IGP. For example, this ISP will run OSPF. This one will run ISIS. So these two ISP A and C will have different routing policy within the IS. So And between the IS, we will run another protocol. This protocol is BGP. Why do we run BGP between the IS? So here we will have BGP, and here we will have also BGP. So running BGP between IS will give to the ISP a control in the routing policy. So BGP BGP have in BGP we can control routing policy more than IGP, and BGP is a scalable routing protocol. So in the next slide we will see why. So BGP, what is so BG? So between us, this pairing is untrust because ISP-A can trust ISP-D. Inside the company, the router trust each other, so they can run OSPF and exchange prefix. But between ISP, the router can't trust each other. So this is why we run BGP. Okay, so the internet in summary, the internet is a set of IS. So what is an IS? So IS is a set of router and prefix or route that are under the same technical administration. So in ISPA, for example, they have 5 administrators. All these administrators will agree on the same policy or in the same routing protocol, and they will administrate their network like he wants. But between IS, they will run BGP. So when they run BGP, they will agree on some policy. For example, ISP-B will permit to ISP-A to travel across his network to go to ISP-C. Okay, so with BGP we can do some filtering policy, and so we can have more granular policy between IS. So what is IS? So IS is the autonomous system. So like we said, it's a set of router and IP prefix that are under the same technical administration, and they have clearly defined routing policy. So this is the definition by the RFC, by RFC 1093. So the IS, how can so the IS the autonomous system, all IS has a number. So this number before 2009, this number was 2 bytes. So it's a value between 1 to 65,534. So sorry. So in this case, there is two type of IS number. There is the public IS number. There the range is from 1 to 64,511, and there is private IS number. It's like IP address that we have public IS number that we can use in the internet, and we have private IS number that we can use inside our organization. So after 2009, there is new RFC for the IS number. It's the RFC 4893. So in this RFC, the IS number are now 4 bytes. So the range is from 65,536 to 4 billion, etc. So we have a bunch of number of IS number. So how do you apply for IS number? It's like IP address. You go to, it's like the IP address. You go to the INA, and you ask for an IS number. But the procedure is more complicated than for IP address. They have a policy for attribute IS number. So you can refer to the INA site for more information. So now let's go into the major topic. So what is BGP? So BGP is the Border Gateway Protocol. It's an open standard so this is the RFC 4271. So what does it mean? That it means that BGP can run in all vendor. So Cisco can run BGP, Huawei can run BGP, Juniper can run BGP. All the vendor can implement BGP, and the implementation between vendor are compatible. So we can have BGP we can run BGP between Huawei and Cisco. So, like we saw that BGP is inter-domain, or the domain is an IS, inter-IS routing protocol. So BGP will run between the IS and exchange route between IS. So this is the primary usage of BGP. BGP is more than that. We can use BGP in multiple things, like MPLS, like VPN. We use BGP. We can use BGP in the data center fabric. So BGP has more than one usage, but the primary usage is the inter-domain routing. So in this presentation, we're gonna focus on the inter-domain routing and in the IPv4 inter-domain routing. So BGP is an EGP. So it's an exterior gateway protocol. What does it mean? There is two types. There is IGP. There is IGP. So there is there is IGP. So here, this is OSPF, we found OSPF, etc. And there is EGP. So IGP ran inside autonomous system, and EGP ran between autonomous system. In the EGP family, we found only one protocol, so BGP. So you can say that BGP is the routing protocol of the internet. So BGP has the responsibility of routing between autonomous system and the internet. So, but EGP, you have not to be confused with the EGP, because there was a protocol before BGP. Its name is EGP. This is the RFC of the protocol. You can refer to it for more information. So EGP is the predecessor of BGP. But this protocol now is not used at all. It's not used. So don't confuse EGP, the type of protocol, with EGP, the protocol. Okay. So EGP, the protocol, is defined in this RFC. So why? So what is the why do we use BGP? We said that BGP is highly scalable. So what is highly? What does it mean? So BGP can handle more than 1 million routes. So and the internet now in 2020. So the internet has more than 800,000 prefix in the internet. You can refer to this site. So when you go to this site, you will see. So here you will see in the BGP table, you can see that in this day there is 800,000 route, more than 800,000 route. This is the IPv4, and for IPv6 there is more. 89472 route, or 8900 route. So here you can say that BGP is the only protocol that can support this number of routes. So OSPF, ISIs can support this number of routes, and BGP has high stability. So in IGP has the capacity of fast convergence. So in OSPF, for example, if a link go down, OSPF can converge less than 1 second. But we don't need that in the internet. because internet have more than 1 million route. So when you have 1 million route, you don't want that when every route get discarded or a link goes down, you need to calculate everything. So your router CPU can't handle that. So this is why BGP is used, because it's the most scalable protocol, the routing protocol. So BGP ran on TCP, so not like OSPF that ran directly in IP. So BGP use TCP. So the port of TCP used by BGP is the port 179. So this is the port of BGP. You need to remember this port because you will need it if you want to permit BGP in ACL or something like that. So BGP, this is the port that BGP use. So when BGP use TCP, so TCP will provide BGP with reliable transport. So we know that TCP has acknowledgement mechanism, so TCP is reliable, and TCP has a sequencing mechanism, so TCP will provide to BGP reliability in order delivery and retransmission mechanism. So we don't need to reinvent the wheel with TCP. So in BGP we just use TCP, and BGP will be provided with all this mechanism. So BGP is a path vector based protocol. So we know that OSPF is a link state protocol. ISIS is a link state protocol. RIP is distance vector protocol. BGP is a path vector based protocol. What does it mean? So path vector protocol has a rich metric, so a very good metric. These metric are called path attribute. So BGP will BGP use multiple metric. This metric is are called path attribute. So the difference between BGP and and IGP, for example, in OSPF, when you want to assign a metric, you will assign this metric to the link, not to the route. So if you want to change the cost, you will change it in the interface. So, but BGP will assign path attribute to prefix or route. So every route has its own metric or its own path attribute. So what we will get, we will gain. So we will gain for routing decision. We can do policy for every prefix differently, because one prefix can have a set of attribute and another will have another attribute. So this is why policy application is easy in BGP. So you can implement policy for every prefix, not the link like IGP do. So the path attribute also provide to BGP a loop of avoidance mechanism or loop prevention mechanism. So there is a path attribute that we will see in the next slide that provide to BGP loop avoidance. So the path attribute is really is very good for BGP because we gain so much benefit with the path attribute. So complicated, for example, complicated policy in OSPF, we can do it in just 1 or 2 lines in BGP. So this is why ISP run BGP. This first reason is that BGP is highly scalable, so he can handle more than 1 million route. So BGP has a very rich metric, the path attribute. So the ISP can implement multiple policy for each prefix, and BGP is highly extensible because For example, when IPv6 came in OSPF, we need to write a new protocol. So we have OSPF v2 for IPv4 and OSPF v3 for IPv6. In BGP, it's not like that. So BGP in BGP, we didn't recreate the protocol. We just add an IPv6 address family, and the BGP work fine. So BGP is highly extensible. So for future usage, if we need to add something to BGP, it's easy to add it. Okay, so like OSPF or like most IGP, BGP need to establish a neighbor relationship. But in IGP in general, so if you want to establish a neighbor relationship between two routers, you need to enable the protocol in the two interface, and the protocol will exchange some hello packet, and the neighborship will go up directly. But in BGP, it's not the case. Because remember, we said that BGP is, and in BGP, we don't trust our peer. So R1 don't trust R2. So in BGP, the neighbor are not discovered. So they must be configured manually on both sides. So in R1, we must say to R1 that R2 that are in autonomous system, for example, number 2 is your neighbor. So and also remember that BGP ran in TCP, and TCP is a point-to-point protocol. So in TCP, we need, if you want to establish a TCP connection, you need the sender need to know the receiver or the destination IP address. So in other terms, so this is the configuration for, you can understand well. So in BGP, for configuring BGP, we just run we go to the system view, we assign a router ID. I will talk about the router ID in 1 minute, and we type BGP1. So the one here is the autonomous system. Okay, so we specify to the router in what is his autonomous system. R1 has an autonomous system of 1. And we say to R1 with this command peer that this IP address, this 10.1.10.1.22 is the address of your neighbor. Okay, and we specify the IS number of the neighbor. So R1 will be neighbor with a neighbor that has this IP address and this autonomous system. We do the same thing in R2. We specify the autonomous system, BGP2, and after that, we use the keyword peer with the IP address of our neighbor and the autonomous system of our neighbor. So in this case, R2 will be neighbor with a peer that has this IP address and this autonomous system. So now how this autonomous system, so how this neighborship will be up. So we said that BGP ran in TCP. So before establishing a BGP neighborship, the two routers need to establish a TCP session. So the R1 and R2 will start the three-way handshake, the TCP three-way handshake. So this is that means they will initiate a SYN ACK, SYN ACK. So the three-way, a basic three-way handshake for TCP. After establishing the TCP connection, the two routers will establish the BGP neighbor relationship. So R1 and R2 will do the TCP three-way handshake. After that, the two router will establish a BGP neighbor relationship. So each router is identified in BGP with a unique router ID. So like the most routing protocol, each router has a router ID. So this router ID can be set manually with this command. So in the system view, you type router ID and you specify the router ID. So the rule is similar to OSPF. If you type the router ID manually, so the router will use this router ID. If you don't specify a router ID, so the router will choose the highest numerical value of his loopback interface. So he will check all his loopback interface and he will choose the highest value. If the router doesn't have loopback interface, the router will choose the highest physical interface, the highest IP address in his physical interface. In this case, if we don't, in R1 for example, if we don't specify a router ID, if R1 has a loopback interface, R1 will choose this loopback interface. In this case, R1 doesn't have a loopback interface, he will choose this IP address as a router ID. So the route, if we don't specify a router ID in R1, R1 will pick 10.1.1.2.1 as a router ID. But it's recommended that you type manually the router ID. Okay. So continue. So after establishing the neighbor relationship in BGP, the router need to exchange prefix, or they need to advertise a route. So in BGP, essentially we have two methods for advertising prefix. So here is this is the two method. We have here R1 and R2. There is a BGP neighbor relationship between R1 and R2. In the routing table of R1 know via OSPF this prefix, and R2 know via ISIS this prefix. Okay, so here there is two methods. The first one is to go to the BGP process and use the network command. So the network command, when you use the network command, you specify the prefix and the prefix length or the mask that you want to advertise. In this case, I said to R1, please advertise this prefix with this mask to your neighbor. Okay, so but when you use network command, this prefix and this prefix length need to have an exact match in the routing table. So in this case, we have this prefix in routing table. For example, if in our routing table we have 23 mask, and here you type 24, BGP will not advertise this route because the route isn't inside the routing table. So when you use the network command, please verify that the prefix is inside the routing table. So the second command is to use the import route command. So the import route command in other vendor, we call it redistribution or redistribute command. So here in the import route, so here we have in our routing table ISIS. So here I make a little mistake. So we have static route. Sorry. So in our routing table we have a static route to this prefix. Okay. So when we have a static route in our routing table, we can say with the import route command, import route static. So you say with this command, you say to BGP, please advertise your all the static route in the routing table to BGP in BGP. So R2 will send all the static route that are in the routing table to R1. So you can filter. So the advantage of using the import route command, you can filter what you want to advertise, because with just this command, you will send all the prefix. So you can use a route policy. You can use a route policy for, and this route policy will match an IP prefix or an ACL. And with this ACL, for example, you will say, I want you make an ACL that match this prefix. And your reference in this import route static, you add route policy, and you specify this route. In the route policy, you specify the ACL. So with the import route, we can filter which route we want to advertise. Okay, so if you want to import OSPF, you type import route OSPF. If you want to import ISIS, import route ISIS. Okay, so in the router, you know that a router has a routing table, and with this routing table, the router will make decision about routing decision. So BGP store all its learned route. For example, when R1 will send this prefix to R2, R2 will store this route in a BGP RIP, or routing information base. So in the router, there is a table when we can find all BGP route, learned route. So this BGP learned route, we will choose the best route in this table. So BGP will launch his path selection algorithm, and he will choose the best one. The best route will be submitted to the routing table. So BGP will send the best route to the routing table. He will say to the routing table, this is the best route that I have. If you want it, you can use it. Because after that, the routing table will see if this route is the best compared to other protocol. Okay. So this is the BGP. This is the BGP RIB, or the BGP routing table. So this is the same example that we used in the last example. So we use this command, display BGP routing table. So how can you read the BGP table? So this is the prefix that we know that we know. So this is the prefix, and this is the next hop that we will use for going to this prefix that the router will use. So when you found 000 in the next hop, that means that this is locally generated route. So in R1, this prefix is locally generated. So R1 advertised this prefix. And here we found the next hop. So in this case, for this prefix, the next hop is the IP address of R2. Okay, so here, when you found a star, that means that this route is valid. What does it mean, valid? Valid is that the next hop is reachable. So this is valid route. Valid route, only valid route can be used in the BGP path selection algorithm. So if a route isn't valid, BGP will not we will not choose that route, and we will not, he will not use it in the path selection. So when the superior sign means that this is the best route. So when you found star superior, that means this is the as a valid route, and this is the best route, and this is and this is and this and this and this is the route that BGP will use for going to this prefix. So star, we said that it means valid route. Superior, it means best route. Here you can find a sum of BGP path attribute. We're gonna talk about this one, the origin. So here the origin, the origin is the last path attribute in the last column. So when you found A, that means that this route was originated or advertised with the network command. And when you found the question mark, it means that this route was advertised with the import command. So, and this is what we did. In R2, we used the import command. In R1, we used the network command. So, the prefix of R2 has incomplete or question mark. When the question mark in BGP, we call it incomplete, and we call it internal. So here we have question mark. So the BGP it was originated with the import route, and it means that it was originated with the network command. So this is how you read the BGP table. So now that we saw how BGP establish a neighborship and how BGP exchange route, we're gonna define what is iBGP and what is eBGP. So eBGP is a neighbor relationship that was established between two routers that are in different autonomous systems. So for example, R4 are in the IS4 and so R1 and R4 will establish eBGP relationship or external BGP. So when we establish external BGP. R5 and R2 will establish external BGP because or eBGP because they are in different autonomous systems. When two routers are in the same autonomous system, the two routers will establish an iBGP in an iBGP neighbor relationship. So how R4 know that R1 is in different autonomous system? Simply because when you define the peer, you specify the IS number of the peer. So the router will compare this IS number with the IS number of the peer. So if the IS number is the same, we are eBGP. If the IS number isn't the same, we are iBGP. So the question is, why do we need iBGP? Why do we need iBGP? So so here in R4, if R4 advertise a prefix, for example, let's say prefix A. So this is a route. So when R4 advertise prefix A, it will send it in an update message to R1. So R1 now via BGP prefix A. So how R1 will send this update to R5? Here we have two two solutions. So the first one is inside our autonomous system, we run an IGP. For example, we run OSPF. So everyone can import or redistribute BGP learned route in OSPF. So when you redistribute the route into OSPF, R1 will send this route to R2 via OSPF, and R3 also will receive the route, but via OSPF. And in R2, we will redistribute OSPF into BGP. So R2 will redistribute the route learned from OSPF to BGP. But the problem here that we will redistribute more than 1 million route into OSPF because it's BGP, is the internet routing table. So this is why we will not use this method. So here, this is why we need iBGP. There is another reason that we said in the update, every prefix has an attribute or path attribute. If we redistribute BGP into OSPF, the path attribute will be lost. So we will lost all the benefit of BGP. This is why we need iBGP. Okay, so iBGP will permit to advertise a route across our autonomous system. Okay.
We cannot hear
The
you
first.
now. Okay, now we can hear you again.
Okay. Okay. You can hear me.
Now we can hear you. Yes. For a couple of
Okay.
seconds, we couldn't hear you.
Okay. So the first rule is that BGP will advertise only the best or the optimal route. So in this case, router A will advertise this prefix via eBGP to RTB and RTC. When these two routers receive this update, the two router will send it via iBGP to RTD. So RTD has two routes in its BGP routing table, one via RTB and the other via RTC. And you saw this two route in this is the two route. So for going to the 100 prefix, RTB has two route. So the first one is the two route is valid because they have the star, and the first route is the best. So the route that are via RT, the route that are via RTB is the best. Here you see that there is an I. The I here mean in the left of the column mean that this is I learned this route via iBGP. When you don't found the I learned it via eBGP. When you found the I, that means that I learned it via iBGP. And here I learned it via eBGP. So RTD has two routes. Okay, but when RTD will send the update to RTE, it will send only the best one. So it will send only the route that has the star superior or the valid and the best. So this is the rule. BGP advertise only the best and the best and the optimal route. How BGP define the best and the optimal route? BGP will run the path selection algorithm across its routing table, and it will select the best of them. In this case, BGP choose this route. Okay. So this is the first rule. The second rule. So the second one is to advertise all all eBGP route to all BGP neighbor. What does it mean? So RTA send an update, eBGP update to RTB. So RTB can send this update to all its BGP peer. So if its peer is an iBGP, he can send it. If it's an eBGP, he can send it. So from when a router receive an eBGP route, it can send it to eBGP and iBGP. So this is the rule. So from eBGP, we can send it. So from eBGP, we send it to eBGP and iBGP. There is no restriction. So RTB can send it to RTD and RTC. So this is the second rule. So the third rule is that when IBGP can send its learned route to eBGP, but we can't. IBGP will not send to IBGP. It's prohibited. So for example, here we have an IBGP neighbor relationship between, we have IBGP session between this RTA and RTC, and RTA and RTB, and RTB and RTC. So there is, so we have full mesh here. Okay, so when RTA want to advertise this prefix, so this prefix, so RTA we send it to all IBGP, so to all his neighbor, to all his peer. So if we send it to RTB and RTC, okay. But when RTB receive an update from IBGP, in this case, it will receive the update via IBGP. RTB can't advertise it to RTC. It's prohibited. And RTC, when RTC receives the update from RTA, RTC can't advertise it to RTB. So this is the rule. Okay. So in this example, I will explain in this example. So here, when RTA send to RTB, RTB can send it to RTD and RTC. RTC receive the update via IBGP. But if RTB has another connection with another router in the same IS, let's say router 1, and there is no IBGP session between RTB and RT1, RT1 will never receive this route, because there is RTC. When RTC receives the route from RTB via IBGP, RTC can't advertise it to R1. It's prohibited. We can't receive the route with IBGP to IBGP neighbor, but we can advertise receive it IBGP route to eBGP. So this third rule is the loop avoidance mechanism of IBGP, because if RTC can advertise the learned route via IBGP to its IBGP neighbor, there will be a loop, because RTC receive IBGP advertisement via RTA. It will send it to RTB. RTB received the advertisement via RTC. It will send it to RTA. We have loop if this mechanism doesn't exist. This is why we don't advertise the IBGP received route to IBGP neighbor or peer. Okay, so here there is you can do it by using a route reflector. But so you can advertise receive it IBGP route to IBGP neighbor when you use a feature called route reflector. But it's beyond the scope of this course. So the rule 4 is that when, for example, the rule 4. So here RTA in the IS 100 want to advertise this prefix. So RTB will receive the prefix. Okay. So and RTB will send it to RTD because we can advertise learn the route from eBGP to IBGP. When RTD receive the route, RTD will advertise it to RTE because we can advertise from eBGP to from IBGP to eBGP. Okay, but for example, if RTE want to, for example, ping this network. Okay, so here the ping will go to RTD. Okay, so the ping will go to RTD. So the destination is 100.0.0.1, for example. So RTD in its routing table know this prefix because he learned it via IBGP. So after processing, after doing a recursive lookup in his routing table, RTD see that I need to send it to RTC. But when RTC receive this ping, the destination is 100.0.0.1. RTC don't know this destination because RTC didn't receive the BGP route. The BGP route are only in RTB and RTD. Okay, so here we have 3 solutions. So the first solution, there is a mechanism that we call it synchronized BGP and EGP. So BGP and IGP synchronization. This mechanism is disabled by default, and you will never use it. So, but how this mechanism work? So in this example, when RTB received the route, he will check its routing table. So when he will check its routing table, if he know this prefix in the routing table, in other terms, OSPF, for example, know this prefix, RTB will advertise this prefix. But if the prefix isn't in the routing table, the router will never advertise this prefix. So in other terms, we need to redistribute or import route from BGP to OSPF. So the IGP need a full view in its so we need a full view in the routing table. So the route that are in BGP, we need this route in the routing table in all our IS, and this is not efficient at all. The second solution and the most used is the second solution is IBGP full mesh. What does it mean? So we will do a full mesh between all our router. So a full IBGP mesh relationship. So we will have we have a peer, RTD will have 2 pair, RTC and RTB, and RTB will have 2 pair, RTC and RTD. So we have a full mesh. When you do this, all your router will have the full view in the BGP routing table. So this case, so the problem is solved because when RTA send the route to RTB will send it to all its IBGP neighbor. So it will send it to RTC and RTD. So question, when RTC receive this route, does can RTC send it to RTD? No, because RTC received this route via IBGP, and when we receive a route via IBGP, we can't send it to IBGP neighbor. Okay, so RTD received the route from RTB. Okay, and the route will go to RTE. So here RTC know this prefix, and there is no problem. The problem with this solution is the full mesh consume a lot configuration. So we will have a very big configuration when we have multiple router inside our network. And also we need to have our backbone router or P router. We need that this router will be performant, because this RTC need to handle the BGP routing table. So this is why there is other solution like route reflector and configuration, and ISP use MPLS. So when you use MPLS, your backbone or your P router will not use BGP. Will not use BGP. So MPLS permit to have a free core BGP. So a core without BGP, and it's beyond the scope of this course. So okay, so let's talk about the BGP path attribute. So we said that the path attribute are the metric of BGP. So there is a ton of path attribute. There is a lot, and this path attribute are categorized in first in two families. We have the well-known attribute and the optional attribute. Well-known mean that this attribute need to be known or identified in all the BGP router. So the well-known family, for example, R1 and R2 and R3, need to know and identify all this BGP attribute, because it's well known. If you want to, for example, Huawei, if Huawei want to do BGP, Huawei router need to know well-known attribute. In the one, but the optional attribute doesn't need to be known by all BGP router. So, for example, R1 and R2 can establish BGP relationship and exchange route. But for example, R2 don't know some optional attribute. So there is well-known attribute. All BGP router need to know this attribute, and there is optional attribute. Not all BGP routed know this attribute. For example, in 2020, we can create a new attribute, and this attribute will be optional. So the new router will identify this attribute, and the old router doesn't need to identify it. The router will ignore it. So a router can ignore an optional attribute. But if the well-known attribute, all the BGP router need to identify it. In the well-known, we have mandatory and discretionary. So what does it mean, mandatory? So when we said that the path attribute are inside the update message. Okay, so inside the update message, So every prefix has a path attribute. Mandatory mean that R1 need for each prefix, R1 need to add this attribute to the prefix. This is the mandatory attribute. There is three. We're gonna see them in the next slide. So when R1 send multiple prefix, this prefix need to have this path attribute. If R1 doesn't send this path attribute to R2, R2 will end the session with R1. So there is no exchange of route, because the update didn't contain the mandatory path attribute. Discretionary mean, so well-known discretionary. So the router need to identify this this path attribute, but the router doesn't need to send it in every update. So for example, R1 can send to R2 an update without this path attribute because R1 don't use this attribute or he didn't use it. Okay, but mandatory, the router need to send it in every update. Okay, so now in the optional we have transitive and non-transitive. Transitive mean that when R2, for example, receive receive an update, so R2 when R2 send the update to R3, transitive mean that R2 need to send this attribute to other autonomous system. That way, this is transitive. Non-transitive, when R1 receive when R2 received R1 update, he will not send the non-transitive attribute to R3. This is and this is optional attribute. If R2 doesn't identify or doesn't know an attribute in the transitive, he will just ignore it and send it to R3. Okay, so this is the path attribute family or category. So there is ton of path attribute. For example, in discretionary we have local preference. So there is a lot of path attribute. In not transitive we have the med. So transitive we have, for example, community. So we have a lot of path attribute. In this presentation we're gonna focus on these three because it's we don't have a lot of time for talking about the other. So the IS path attribute. So eBGP loop. So the first path attribute. It's well known, so all BGP router need to know it or identify it, and it's mandatory. So in every update, the router need to send this path attribute with the update. So here we have eBGP neighbor relationship between these four routers. So eBGP loop avoidance mechanism is the IS path attribute. So in this case, for example, when R2 send, so this is we're gonna see the loop avoidance mechanism of eBGP. So R2 send an update to R1 and R5. Okay, so when R5 receives the update, he will send it to R4. And when R4 receives the update, he will send it to R1. And when R1 receives the update, he will send it to R2. So there is no rule that prohibit R1 to send the update to R2. This is not like we saw in IBGP. So eBGP, when eBGP receive a route from eBGP neighbor, it can send it to all its neighbor. So this is the solution. So the inventor of BGP said that when I send the update, for example here, I will record the IS from where the update came from. So in this case, so R2 in the IS path attribute, he will put 2 because it's IS number. When R1 receive the update inside the autonomous system, the path attribute will not change. So for example, if the route inside IS1 will go in multiple path attribute, when this route leave the IS1, so this route will go to IS4, R1 will add its IS, and we read it from right to left. So so R4 will know that this update came from IS number 2 and pass via IS number 1. When R4 send the update to R5, he will do the same. He will add its IS number. So when R5 receives the route, he will send it to R2. Okay. So he will say pass via 5, 4, 1, 2. Now this is the loop avoidance mechanism. When R2 receives the update, he will check if its autonomous system is inside the IS path attribute. So far, he will check to it's my autonomous system. So this update came from me. They came from me. So R2 will, so a router will not accept a route if he found its autonomous system inside the route. So when R2 receives the update, R2 will discard this update. So this is how BGP use the path attribute for avoid loop. So the second path attribute is the next hop. So the next hop, so here the next hop, so next hop change from if we are eBGP or iBGP. So in this case, for example, RTA will send this prefix to RTB via eBGP. Okay. So when the next hop that RTA, because the next hop is a path attribute that are well known and mandatory. So in every update, the router need to specify the next hop of the update of the prefix. So RTA will send to RTB an update. Okay, this update has this prefix. Okay, so this update has this prefix. In this update, RTA we say the next hop of this prefix is this IP address or 10.1.12.1. So when RTB receives the update, RTB will send it to its eBGP neighbor and iBGP neighbor. So when eBGP send a route to iBGP, the next hop is unchanged. So when RTB send the route to RTC, RTB will not change the next hop. So if you do display BGP routing table in RTC, you will see that the next hop is unchanged. Okay, in the routing table of RTC, we will see that if you want to go to 100.0.0.0, you have to go via this next hop. When a router send a route to via eBGP, the router will change next hop. So in this case, when RTB send an update to RTD, the next hop will be this interface of RTB, because this is the interface that we used in the BGP, in the eBGP relationship. So in this case, in RTD, we will see that the next hop is this interface, this other IP address. This is the IP address of this interface. So in summary, when a router receives an update, when the router sends the update to iBGP neighbor, the router doesn't change the next hop. When the router sends the update to eBGP neighbor, the router will change the next hop. So by default, we said that by default, that when RTB send the update to RTC, the next hop is unchanged. But we can face some problem because RTC don't know, if RTC don't know this next hop. So in this case, we want, for example, we can say to RTB, there is the option to say to RTB when you send the update to RTC, please change the next hop to your interface. So there is a command when RTB send the update to RTC, RTB will make the next hop his interface. Okay. So the last attribute is the origin that we saw. So in the origin, when a route, we said that when a route is advertised with the network command, we have the flag A internal, and when a route is advertised via the import route command, the flag is a question mark, and we call it incomplete. Okay. So now let's go to the lab. So this is the lab.
Do you want to take some questions before the lab or after?
I think after the lab, because we don't have time. So
yeah,
if we make the question now, we will have to do
okay.
more.
Yes, okay, I agree.
Okay. Or we can we can allow 2 questions or 3 before starting the lab, like you want.
Okay, does anyone have a question? If you have a question, you can use the raise hand option. If you don't, we'll wait. Okay. I see we have a question. Hello, Mihail.
Hello, dear colleagues. Thanks for this presentation.
Thank you.
Walid, I saw that you used private networks for describing eBGP relationships. Why do you use these local networks as an example?
I understand. Oh, sorry, 1 minute. So in the ABG,
yes. You can stay at this slide. Yes, or
yes, this one.
slide.
Yes, this one. Yes.
When on this picture, here a link eBGP between RTA and RTB, you use the local private network for describing it. Why do you?
So in the real world implementation, the link between the eBGP link is we use the public IP address. In this example, it's just a lab, and so I use the private IP address just for lab. But in the real world, you will see that here we use a public IP address between the 2 routers. So yes, you are right.
Okay, and when we use the network command to share additional network segments, do we need to use also the public IP addresses, or we can use private network segments?
You can't advertise. You can't advertise private segment inside. So if you run BGP inside your organization, you can use what you want. So, but if you run BGP between 2 ISP, you will advertise public routable IP address.
Yes,
so,
correct. I just want to confirm it, because in this slide you're also use internal addresses.
Yes, it's just for the purpose of the explanation. I use the private IP address.
Thanks, I got. Thanks.
No problem.
Okay. We have one more question.
Yes.
Hello?
To know the well-known dictionary. So can you explain one more times?
Okay. So well-known mean that the all BGP speaking router need to identify this attribute. So for example, so if we have, for example, in discretionary we have local preference, all BGP speaker need to identify and know the local preference attribute, because local preference is well-known discretionary attribute. But the difference between mandatory and discretionary, when you send an update to your peer or neighbor, so the mandatory, you have the well-known mandatory, you have to send this attribute into each update. But the discretionary, you don't need to send this update, attribute in each update, because the real difference is that if R1, for example, send an update to R2 without the well-known mandatory, this is not the R2 will not accept this update because it doesn't contain the well-known mandatory attribute. But if the update doesn't contain the well-known discretionary, R2 will accept the update. Okay.
Okay. Thank you.
Thank you. Okay.
One more question, or
One
we
more.
can,
I see that we don't have any more questions.
okay. So this is the lab. Here we have 4 AS and AS1, 2, 3, AS4, AS6, and AS5. So I already configured all IP address. So between each router, for example, between R1 and R5, there is an IP address of 10.150, and all the interface of R1 and with 1, and all interface of R5 and with 5. I specify it here, and every router has a loopback interface. With the loopback interface of RX is XXXX32. So for example, R1 has a loopback interface of 1.1.1.1/32. So I already configured OSPF inside IS123, and I already configured eBGP relationship here. So between R6 and R5, R6 and R4. So what we're gonna do? We're gonna configure eBGP between R5 and R1, and R4 and R2, between R4 and R2. And we're gonna configure iBGP between R1 and R2. Okay, and we will advertise loopback 0 of R6. So let's get started. So let's start with R1. So we said that we will configure the eBGP between R1 and R2. So first step is to go to the system view. We type BGP 123. So here you can use only one process of BGP in your router. If I tap BGP 1, they will say that BGP is already running with the IS123. So you can run only one instance of BGP. Okay, so in this case, we run the, BGP in the IS123. So here, I will use the peer command, and I specify the IP address of my peer, or R5, 10.1.5.5. So this is a private IP address. In the real world, you will have a public IP address, but just the case for the presentation, I make the IP address simple so you can understand that this link is from R1 to R5, and this is the IP address or R5. And use the keyword IS number for specify the IS number of your peer. In this case, is 5. Here, I configure the eBGP from R1 perspective. So now we go to R5 and we will do the same. So BGP 5 peer 10 1 5 1. The IP address of R1, IS number 1. So now the relationship between R1 and R2 is configured. So the relationship, the neighbor relationship will be up soon. So BGP is very slow routing protocol. So it needs some for verifying if your BGP session is up. Use display BGP peer. So here, sorry, I have 2 BGP session. So this one is with R6. The session is established, but with R1 is idle. So the session isn't established yet. So let's verify R1. Also, the session isn't established. Okay. So the session don't want to be established. Sorry, we have I make a mistake in the IS number in R1. So here I make a mistake when I type the IS number. I type 1, and so it's my mistake. So I will undo this pair, and I will make this the right autonomous system. IS number 1, 2, 3. Now it will work. So you have to match the IP address of your peer and its IS number, unless the peer will not work. Verify the peer is established now. So BGP is slow, so you can use this command, display BGP peer, for verifying your configuration. In this case, my router ID is 10151. The local IS number is 123, and the number of peer is 1. And the relationship with R5 is established. Okay, so now and also there is some information. So we use BGP version 4, and the IS number of our peer is 5. So let's do now the eBGP relationship between R2 and R4. Let's start with R4. Same thing, we type BGP 4 and peer 10 2 4. This is the IP address of our neighbor, or R2, and the IS number is 1 2 3. Okay, so and we do the same in R2. peer 10 to 4 for IS number, the IS number of our peer 4. And the BGP relationship will came up between R4 and R2. So after that, we will create an IBGP relationship between R1 and R2. Okay, so the BGP relationship between R2 and R4 came up. So we have the state established. So the BGP session is established, and we run BGP version 4, and this is the IS number of our peer. So in R2, we want now to establish an IBGP session between R1 and R2. Same thing. BGP 1, 2, 3. Now, here there is, when you establish an IBGP session, there is two ways. You can establish it with the physical interface of the two router, and there is a more efficient way. We will establish the IBGP relationship with the loopback interface. Okay, why? Because if we have a link between R1 and R2, when you enable the BGP relationship with the loopback interface, so for example, if you use the physical interface, we enable BGP with this interface. So if this link goes down, the BGP session will go down, and we have another link. So when you use the loopback interface in the IBGP neighbor relationship, so if a link, this link go down, the session remain active because R1 has another path to R2. Don't forget, it's TCP session. So when TCP session, so when R1 will go to R2 via the best path in the routing table. Okay. So this is why we use the best practice is to use the loopback interface in the IBGP. So let's do that. So in our case, R2 has a loopback interface of 2222, and R1 loopback interface of 1111. So BGP 1, 2, 3. Here we say peer 111, IS number 1, 2, 3. Okay, so we will do the same in R1. Okay, and the peer will not came up because we need one more command. I will talk about it. So here BGP 1, 2, 3, peer 2222, IS number 1, 2, 3. So how R1 know that this peer is IBGP relationship? He will compare its autonomous system with the autonomous system of its neighbor. The same, so it's IBGP. So here the peer will not came up. Why? Because because in the peer will not came up because why? Because R2, for example, R2 wait for a TCP connection from which IP address? R2 wait for a TCP connection from 1111. So if the TCP connection don't came from 1111, R2 R2 don't know if what is the IP address of the other interface of R1. But in this case, when the TCP connection is initiated, so R1 will make this IP address as the source, because when, for example, when you ping from R1 to R2, for example, from R1, I ping 2222. When the ping, the destination, what is the destination? Is the IP address 2222, but the IP address is 2222. So the of R2, but the source, what is the source? It's the IP address of the outgoing interface. Okay, so R1 will use this IP address as the outgoing interface. Same thing in the TCP, BGP TCP connection. R1 will use this IP address when he will establish a TCP connection to R2. So we need to tell our router, please use your loopback interface as source when you establish BGP connection with this peer. So here, how we can do that? We go to the BGP configuration and we say with this peer, with R2, please use loopback 0. This is the command, connect interface loopback 0. You say to R1, please use this IP address, use this interface use loopback 0 as your IP source IP address. We do the same with the R2. BGP 123 peer 111. We say to R2, please, when you establish TCP connection with 111, use this, use loopback 0 as your source IP address. So here you will see that the neighbor will came up, okay? Because now the two router will do the TCP connection with their loopback interface. So it's idle. We have now it's up. You see when we add this command, it's up. Now, if you do the command in just one router, there is a chance that the TCP connection will be up. But this is not recommended. Please do this command in the two sides, in both sides, because in TCP there is a mechanism. So there is a client and server. So so you have in reality you have to use this command only in the client side, the TCP client. But in some case you don't know who is the client, who is the server. So please just use this command in both sides. This is the recommended way of Okay, like we did. We use this command in the both sides. So here we establish IBGP between R1 and R2. Now we advertise loopback 0 of R6 in BGP. So we go to R6. So R6 is pre-configured. So I configure BGP in R6. So display BGP here. You can see that R6 has two neighbors, R4 and R5. So for advertising prefix, we use, for example, network command. But I will advertise this prefix. Here, before advertising this prefix, check your routing table, display IP routing table. You have, in your routing table, you have to have this prefix with this mask. In this case, I have this prefix with this mask. If here I type 30 or 24, BGP will not advertise this network. The network command need an exact match. So now let's verify that R6 will advertise this command, this prefix. Display BGP routing table. So here we have R6. When you see that the prefix is added to the BGP routing table, mean that R6 can advertise it. So the next hop 0000 mean that I generate or originate this route locally in R6. This is the origin code, mean that I originate this route with network command. Okay, so star and superior mean that this route is valid and this is the best. Now that I advertise loopback 0 of R6, R6 we send it to R5 and R4 because it's eBGP neighbor. So in R5, in R5 display BGP routing table, we have 6666 via this R6, and see the path attribute. The path attribute change. Now we have 6i. So if you this is the path attribute. Now R5 will send it to R1. Okay. Display BGP routing table. R1 has two routes to reach R6. One via 10155, this router. He learned it via eBGP. Okay, so this is the next hop. It's this IP address. Okay, and this is the best, the valid route and the best. And see the path attribute. R1 know that this route was originated with network command in the IS number 6, and IS number 6 send it to IS5, and from IS5 it go to its IS. So here the second route came from R2 because R4 received the update via eBGP. R4 send it to R2, and when a router receives a route with eBGP, he can send it via iBGP. So R2 send the route to R1 via iBGP. So, but here the route isn't valid. Why? Because the next hop is unreachable. So if you check in the routing table of R1, you will not found the next hop. So if you check in the routing table, make a mistake, sorry. So I repeat, when you check in the, you see that the, BGP routing table. Here you said that next hop is 10.2.4.4. So when you check in your global routing table, IP routing table 4.2.4.4.4, so R1 don't know this route because R1 don't know this prefix. Okay, so this is why this route is not valid. So how can we make this route valid? So here there is two solutions. The first one, in R2 we can advertise this prefix via BGP or via OSPF. The second solution is that we said that when eBGP send a route to eBGP send to eBGP, the router can change the next hop. But when R2 received the route from eBGP and he sent it to iBGP, R2 can't change the next hop. So R2 can't change this next hop. This is why R1 see the next hop is the next hop is 10.2.4.4 or this interface. So we will say to R2, please, when you receive a route and you send it to R1, change the next hop at your IP address. How can we do that? So in R2, you go to peer, you say peer 1111 to this neighbor, make the next hop local. This is the full command. Wait 1 minute. Let me make it clear. So peer 1111 next hop local. So R2, we say to R2, when you advertise prefix to 1111, please make the next hop, make your IP address as the next hop. We will say the same thing in R1. So R1, when R1 send the update to R2, he will make itself as the next hop. So peer 2222, make yourself the next hop. Okay, so now if you see the BGP routing table, you can see that the next hop change. Now the next hop is 2222 and the route is valid because the next hop is reachable now. But this next hop is the best. Okay, but now the route is valid and we can use it. In R2, same thing. So this is R2. You have two routes. So the first one via R4 and the second one via R1. Okay. So the best route is via this next hop or via R4. But the route via 1111 is valid. The I is mean that this route is learned via IBGP. Okay. So now if you check in R4, R3, so R3 don't know R3 don't know the 6666 because R3 don't run BGP. So here the solution is to run is we talk about that is to have a full mesh. What does it mean? So here we will have a full mesh. So R3 need to run BGP. Okay, so we configure BGP in R3. So if R3 don't run BGP, so the R3 will not know the 6666 prefix. So the R3 can, so all traffic going to R3, so all traffic going to R3 will not go, we can't go to outside the autonomous system because R3 doesn't have the BGP table view. So the solution is to have a full mesh. Let's configure that. BGP 123 peer 111 IS 123 peer 222 IS 123. So I have two neighbors, 111 and 222. So I will add the connect interface feature. So I said to R3, please use your loopback interface to establish the TCP connection with the two other routers. So this is what I need in R3 for establishing the BGP IBGP relationship with the other router. So I go to R1 now for establish with R3. Same thing. And we add also the next hop local command. So when R1 send update to R3, he will make its IP address as the next hop. We do the same thing in R2. Here, IS123, here, connect interface, loopback 0. And last here, when you send an update to R3, make yourself as the next hop. Now we will have a BGP neighbor relationship that will came up between R3, R2, and R1. Here in R3, so established in R1, active in in R2, but now it's up. So now we have the peer relationship is established for both router. Now R3 in its BGP routing table has the route. Okay, so he has now R3 know the 6666, and R3 choose router 1 as the next hop. Okay, so now we can the last thing now we want we received the route from R6 in R3, but you see that using the full mesh IBGP is time consuming, because if you see the current configuration for BGP in R3, so for just 1-2 peer, we have a lot configuration. This is why there is another solution. It's the router reflector and configuration. But it's the most router reflector is most used because it's less complex than configuration. Now we want to ping from loopback 0 of R3 to loopback 0 of R6. The problem is that R6 don't know the loopback, don't know the network 3333 or the loopback 0 of R3, because we didn't advertise it in BGP. So if we do display BGP routing table, R6 don't know the 3333 network. So in R3, we will advertise the network with the network command, the prefix 3333. Okay. So the mask is 32. Now in the BGP routing table of R3, we can see the next hop is 3333, the route 3333. Now in R6 will receive this route. So here we have, okay. So here it's time to talk about something. So here we have a RIP failure. I will explain you what is a RIP failure. So here we have, when we advertise from R3 to R1, so when we have here we have the next hop is we have this route 3333. So this route is learned in R1 via OSPF. So when R1 see that this route is learned via OSPF, we have a rip failure. So R1 will not advertise this route to its neighbor. So the solution of this problem is to advertise the route in R1 because in Huawei router. So we have to advertise this route in R1 or use another next hop. So use another next hop in R3, for example, for not having this pair. So 333 in the network and in the next hop. So when you advertise 333 in R1, R6 will receive it. So let's ping from R1 to R6. So we have to source our ping. So we will say, please ping. Use the source IP address of loopback 0 when you ping R6. And you see that the ping pass to R6. So last, it's this is bonus. So Huawei define a proprietary attribute. We call it the preferred value. So the preferred value is work only in Huawei router, and it's local attribute. Okay, so it's a local attribute. So what is the preferred value? So in a BGP routing table, every prefix has a preferred value. Okay, and higher is better. Okay, so this is the preferred value of all the prefix. So here, for going to 666, R3 use R1. Okay, I want R3 use the only for this prefix for going to 666. I want to R3 pass via R2. Okay, so I want to R3 pass via R2, not R1. We can use the preferred value. So we will change the preferred value of learned route via 222. Okay, how can we do that? So we need to apply a BGP route policy. Okay, so when you when you specify the peer, when you specify the peer, use a route policy. Okay, so the route policy, we didn't create it yet, but the route policy is a mechanism for in BGP for creating policy and filtering a route. So before we apply it, we need to create it. So we create a route policy. So the name of this policy, we will call it BGP, and here we will permit node 5. So permit node 5 is to create a sequence in the route policy. Okay, so if match, we will reference an IP prefix, and my IP prefix, I will call it BGP. Okay, so if it's match the IP prefix that I will create, I don't create IP prefix yet, apply. So apply. Here you can see that we can change the IS path or multiple path attribute. But in my case, I want to change the preferred value. So I say apply preferred value, and I give a value. In this case, I will give value of 10. I create the IP prefix. because the IP prefix is not created yet. So the IP prefix has BGP permit 666. I will match the network that I want to permit. Okay. Now, summary. I create a route policy. I call it BGP, and this route policy will match this IP prefix. So match this route, and if when it match this route, it will apply a prefix value of 10. So the last step is to apply it. You go to the BGP process, peer. So I want to my traffic pass via 2. So I say to 3 when the peer 2222 send you a route, please apply this policy. Which policy? BGP import. So when you receive the route, please apply this policy. So R3, when R3 receive the route learned via R2, R3 will see if the route received match the route policy, and the route policy match the IP prefix, and the IP prefix match 6666. So when R3 receive the route, he will, what R3 will do, will change the prefix value of 210, and the path of R3 change. So R3 will go via 2222, not 1111. Okay. So here we change the route path selection with a proprietary path attribute. We call it preferred value in Huawei, but this path attribute has local significance. So it works only in the router when you configure it. So R1 and R2 will not be affected by this change. Okay. So this is our lab. So now I go to the presentation, and so if you have question, and I take so Mrs. Elena will take the place.
First of all, let's see if anyone has questions. You can raise hand. And thank you for all of you who managed to stay online with us
Yes,
until
it's
now.
very long webinar. Yes, it's very large topic, and we can't cover everything.
Yes, it's but a few users asked me to share the recording after, and I want to tell everyone that we will share the recording after the live session. You will be able to find it on the Huawei Enterprise Community, forum.huawei.com. But now, please let us know if you have any more questions, or we can proceed to our questions. Okay, I don't see anyone raising their hands, so I just want to make a quick introduction of the forum if you don't know it already.
Okay.
The Huawei Enterprise Community, a technical community for all Huawei products and certifications. We already have over 167,000 members. We have over 43,000 posts that you can learn from. We invite you to post there, to share your skills, to share your knowledge, to ask questions, ask solutions to technical issues. And also, just so you know, we also reward the most active members of the forum. We reward those who share their skills, who share their knowledge. We have different types of rewards. We have the MVE program, which stands for the most valued engineer. And high coins, which are basically the internal currency of the forum that you can use in exchange for the rewards that we have in the online mall. Also, we have monthly activities with different rewards, which include exam vouchers, Sometimes we even have different types of gadgets, Amazon gift cards, and different types of other rewards. And also we have live webinars each month, and as you can see, there's a lot to learn from them. Yeah, like I was saying, people are still asking me. Yes, we will post the recording, the training materials after the session. So Walid, it seems that people are really interested in your presentation, but some of the users weren't able to stay until the end, so they will be able to find the trainings on the Huawei Enterprise Community. Okay, can you please move to the next slide? Okay, guys, yes, this is how the webinar post looks like in the forum. You can either search it directly using BGP fundamentals and configuration in the search bar, or you can see the direct link in the presentation. You can go to forum.huawei.com and you can find the webinar on BGP fundamentals. Walid has prepared 3 questions for you based on the presentation, and we will also post the questions there in the forum. 10 users who reply all the 3 questions correctly will have a chance to win a $20 Amazon.com gift card. And also Walid will choose some of the questions that were already posted in the forum, and we will reward the 3 users with 50 high coins. I'm not sure if we still have questions if we still have time to answer those ones as well, but maybe you can answer them in the forum.
Okay.
But if you found an interesting question there, you can.
I think the most question was
covered
answered through the webinar. Yes,
yeah, that's great. Yeah, I think that as well. So we will just announce the users that that won the high coins. Okay, guys. So this is the webinar post in the forum. This is how you can recognize it. You can also search it by its title. And now Walid will present you the 3 questions that you have to answer in order to get the chance to win.
Okay. So this is the first question. It's a one choice question. On top of which protocol does BGP run? And you choose one answer. So this is the second question. Which of the following attributes are BGP well-known mandatory attribute? So there is 2 correct answers. And the last one is, what kind of BGP session is established between 2 routers that are adjacent but in 2 different autonomous systems? There is 1 answer.
Okay, so we have a single choice, a multiple choice, and another single choice question.
Yes. So if they have question now, we can.
Sure. So if any of you guys are still here and have a question for Walid, now is the time to let us know.
Have enough energy to.
Thank you, by the way, for your time. I don't know if anyone has any questions, they can also post them in the forum.
Okay.
But for now, I see that no one has any questions. So this means that you covered most of the things that they wanted to know.
Thank you.
I hope that it's not because. Okay, I think everyone knows how to use the raise hand option, so that's not a problem.
Okay.
Okay, so if no one has more questions, we will announce the winners in the forum. We will allow users to reply your 3 questions there, and we will announce the winners 5 days after that, I think. And also we will announce the winners who posted the best questions. And this was it for now. As you already know, we have a new webinar each month, and we'll let you know what comes up next month. And as I said before, you will be able to find the recording also on the Huawei Enterprise Forum. So in case you weren't able to join this live session, or if you want to share it with other colleagues as well, that's where you can find it. Okay. Thank you, Walid, first of all, for your time and effort.
Thank you.
And, for your presentation. Thanks everyone for watching, and stay tuned for more.
Thank you.
Thank you. Bye-bye, everyone.
Thank you.